Section 1.2, some mathematical models. So how do we use like differential equations in physics or chemistry or bio? We did actually look at one example before when we covered math 3A, calculus 1, and we repeated again in more in depth in calc 2, 3B. But today we're going to go more into this. Recall from before, we recall the first thing is S of t is the position function. We have V of t is the derivative of S of t, that's the velocity, and A of t, which is the first derivative of V or the second derivative of t, that's the acceleration. And this can be written in a different way, d square s dt squared, so the second derivative of s with respect to t, or dv dt. Other things to recall, weight is mass times gravity. And we have Newton's second law of motion. What does it say? Well, it says that the force or the sum of the forces is mass times acceleration. Sum of the forces acting on an object is the mass times the acceleration. Sometimes you might have an object here and there's some force being applied down, let's say like mass times gravity, and let's assume this is the positive direction, therefore that's a negative. And then there's another force going up, let's call it K. Then in this case, the force being applied on this object is going to be the mg down and minus, because K is heading up, K equals m times the acceleration. And one thing we can do here with this acceleration, you can rewrite the acceleration as dv dt. It's the derivative of the velocity. And what we can do, we can move the keep m times dv dt the same, subtract mg and keep negative k the same. Or you can swap it. There's so many ways to rewrite this. You can put the k here and mg on the other side. And most likely we can divide by m to get a differential equation like so for v dv dt. That's a differential equation. So Newton's second law of motion, it helps us to start the problem F equals m times a, and depending on what they give us for a or what is given for the force, especially the force, and then from there you can see what they're asking you to prove something or verify something or try to find a differential equation. But that's how all these questions are solved. Now another thing we need to recall, when we say x is directly proportional to y, means x can be written as k times y, where k is a constant. Also, x is inversely proportional to y, means x equals k over y, where k is a constant. Sometimes, they give you, let's say a, the acceleration is given as d squared r dt squared. It doesn't have to be s all the time, but it's just the second derivative of something, let's say. And let's say a is given as k over r squared. We need to write a differential equation in r. So we start with a, which is d squared r dt squared. It's a, right? It's a. And a is given as k over r squared. You can leave it like this. And if you were able to find what k is, then you can substitute that in to get the differential equation you need. That's just an example about how you put equations together to form a differential equation in a specified variable, in R or whatever it is. The other thing, good to know, E of t so here we have R, we have L, and we have C. So C is for capacitor, R for resistor, and L for inductive or inductor. Okay, what do we define them as? We define them as the inductor L di dt, L times di dt. What is I here? I is the current in this circuit, and we define I to be always dq dt. T is the time and Q is the charge. It's physics stuff. So here, how do we rewrite this? If I is dq dt, then di dt is the derivative of the dq dt, d of I is dq dt, and this can be rewritten as L d square q dt square. For the resistor is I times R. R stays the same and I is dq dt. We have the capacitor 1 over C times R. So what I'm showing you here is just how we apply physics within the differential equations. If we add all of them up, add everything up, what do we get? L d square q over dt square plus R dq dt plus 1 over CR, and that would give us E of t. That's the voltage. Good to know. If any of those things is missing, let's say if R is missing, then the part that has R would be gone. If L is missing, the part that has L would be gone. If C is missing, the part that has C would be gone. So let's look at an example. So that's E of t. Different circuits, they have different given information. Let's look at this figure. We need to find a differential equation. I'm gonna abbreviate it with DE for this circuit. How do you find that out? So basically, we need to find out a differential equation for that. Remember, I of t is the current. So I from earlier is dq dt. So di dt is d squared q dt squared. That's what we just did earlier. And we had the differential equation E of t, the one we found, L d squared q dt squared plus R dq dt. So let's say we would like to find the differential equation for this circuit for I of t, for the current. What is that going to be, the differential equation? So this one, I wrote E of t equals L d square q dt square plus R dq dt. Of course, plus 1 over c, but there's no c in here, so it's this, the c is gone. Okay, the c is gone. But then since they're saying, so here again, no c. Since they said it's going to be a differential equation in I, so what we're going to do is, one thing we can do here is leave this the same. D square q dt square is this one, di dt. So it's di dt plus r. This one is I. That would give us the differential equation we're looking for. Another slightly different kind of example. Let's say we know that f equals m times a, that one we went over earlier, and also f is the derivative with respect to t of m times v. It's given that negative mg equals m dv dt minus v dm dt, and m of t is m0 minus a times t. We would like to find an equation. We'd like to get an equation, or actually find a differential equation. Find a differential equation for v. If v is negative b, this v here is negative b. Note a, m0, and b are all constants. So what do we need to do is, so when we say m, this means m of t, m of t. So I can replace those in there. So replace this in there. So negative, instead of m, it's m0 minus at g equals m of t is m0 minus at. And then we have the dv dt stays for now. We can keep it the same. Minus that v is negative b. And what is dm dt? dm dt from here, dm dt is 0 because that's a constant, minus a times 1. So it's negative a. You can leave it like this, or you can just try to simplify this out. So you can multiply this, negative m0g plus atg equals m0 minus at times dv dt minus ab. So then you can leave it like that, or add ab to both sides. So ab minus m0g plus atg equals m0 minus at stays the same, and dv dt. So what we did, we found an equation in v, means this must be v there with respect to time, with respect to anything. That's what we did earlier. We found for I, a differential equation I, so we need to have a di dt, the partial derivative.